Okay, good morning, all of you. Now
All of you,
the
please switch off your mics, please. Sir, Jagdish, sir. Yeah, please.
good morning, all of you. Today is the fourth day of the session, and first session is from Dr. Dhanya. She is presently working as an associate professor in Department of Civil Engineering, Indian Institute of Technology, Delhi. Her research interest includes hydroclimatology, hydrologic extremes, water resource management, land surface modeling, and many more things. Dr. Dhanya's research attempts to generate fundamental scientific understanding of hydrological extremes along with improvising of the hydrological modelings to provide early warning methods and adoption policies for sustainable water resource management. She is the recipient awards of NASI Young Scientist Platinum Jubilee Award during the year 2017, Young Research Award 2017 from Ministry of Earth Science, IEI Young Engineers Award 2016-17 in Civil Engineering discipline, Young Associate of Indian Academy of Science, and Professor N.S. Govindrao Gold Medal for the best PhD thesis in the Department of Civil Engineering at Indian Institute of Science, Bangalore for her doctoral research. She also serves as the editor of journal Earth System Dynamics by EGU and as the associate editor of Journal of Earth System Science, Sadhana, Friendliness in Water and IEI series a journal. And along with that, she is having a number of publications also, and she is a very dynamic lady. And now I invite Dr. Dhanya to give her first lecture series of extreme precipitation event modeling considering non-stationarity. Dr. Dhanya, please, you can start your lecture.
Thank you so much, Jyothi ma'am, for the generous introduction. And good morning, everyone. Am I properly audible?
Yeah, audible.
Yeah. So let me make it full screen. So the topic of today's discussion is on extreme precipitation event and how to model it, considering the aspect of non-stationarity. So before starting this lecture, the extreme event modeling is going to be a mathematically intensive topic. But then for a presentation like this with a limited duration, it is very difficult to explain all those mathematical concepts. And the equations, complex equations. So what I have tried in this lecture is to give you an idea or glimpse about what exactly this topic is, and if you are taking up this topic, then how to handle it without going much into the mathematical intensiveness. But I must say now itself that at some places we may come across some equations which is unavoidable. So wherever it is unavoidable, I have put some equations, but then I have tried to simplify that as much as possible. So how we are going to going to go through this lecture is that we will first of all start from the very basics, what is extreme events and how to handle it, what is stationarity and what is not stationarity, and why we have to worry about that, why we need to focus on these aspects, and then we will move on how to model it, and when you model it, what are the aspects you have to take care of. That is how we are going to go through this lecture in the next 1.5 to 2 hours. So starting with extremes, as you know that extremes are very rare. That is one advantage, but the disadvantage is that whenever it occurs, it has a very devastating effect on the society and the economy. And the rarity of these extremes make it very difficult to even understand the characteristics of this, or rather to model it. So rarity in one way it is an advantage, and another way it is a disadvantage, because we have only a limited data of the extremes to model the extremes. Now extremes are often, if you want to pick up the extremes, the definition of the extremes is an event which is occurring above or below a certain threshold. So, and also the extremes depends on the geographic content also. For example, Delhi, we are accustomed with this kind of high temperature and the low temperature, that is hot extremes and the cold extremes. But then these hot extremes may even be termed as a heat wave in temperate regions. So depending upon the geographical context also, the definition of these extremes vary. So as I mentioned, often the extremes are picked up as a value above or below a threshold value. But then if we get a time series of a variable, for example, precipitation or rather temperature, what we do is we draw the probability distribution function of that particular variable, and we look at the values which are lying in the tail of that probability distribution function. And what is this probability distribution function? PDF. Probability distribution function are nothing but, if you have a time series, all we can do is to try to draw a histogram. We arrange these time series into various ranges, various bins. For example, if the time series, the minimum value is 0 and the maximum value is 100, we can classify that, categorize those values, that is from 0 to 10, 10 to 20, like that. And we put all the values which are lying between 0 to 10 in that bin. So in that bin, the number of occurrences gives you the frequency of the event, right? And that frequency divided by the total number of occurrences should give you the relative frequency of that event. So this relative frequency is nothing but will give you an idea about the probability of events falling in that bin. So if you draw a relative frequency histogram, as I have shown here, let me take out the pointer also. So here, as I have shown here, these bar plots, these are the relative histogram values. So if you draw the relative histogram when you get a time series, that should give you an idea about the shape of the probability distribution function. And if you are sticking to the relative histogram and then draw the blue line like this, then that is something called empirical probability distribution function. And this empirical probability distribution function is strictly based on the time series and the relative frequency or the probability of occurrences of each of the events in falling in that particular bin. Now, there are something called theoretical PDF. So if we see that this empirical PDF or the shape of the relative histogram is falling close to any of the PDF function already known to us, that means you must be aware of the frequently used probability distribution functions like normal distribution, which follows a bell-shaped curve, and log normal distribution, the exponential distribution, gamma distribution, etc., etc. So if you feel that the relative frequency histogram is closely following the shape of any of the known distributions that is known to us, then then we can fit a theoretical PDF curve to these particular time series value, right? And then, for example, theoretical PDFs are often expressed something like this. For illustration, I have given the theoretical PDF or the PDF functions of normal distribution and the exponential distribution. Here, I want to make some points here. So theoretical PDF is nothing but you can assume that it's equivalent to curve fitting. There is an equation with you and you are fitting this particular relative frequency or the curve with respect to this particular already defined equation. So if you look at the normal distribution, it is fx. Fx is the small f. F is the usually how we represent the probability distribution function, and capital F, if it comes, then it means the cumulative distribution function. So fx is equal to 1 by sigma root by e raised to x minus mu the whole square by 2 sigma square. So if you look at this equation, if you do not worry anything about this, but this is just an equation, then x is the variable you are dealing with. That x is the time series you are dealing with, maybe precipitation or maybe rainfall. And then there are two constants here, that means mu and sigma. Mu and sigma, so the constants like this, we call that as the parameters of the distribution. So we have to find values for these parameters. So for example, if you look at the normal distribution, we have seen that there are two parameters in this distribution for us to estimate. And if you look at the exponential distribution, this is lambda e raised to minus lambda x. Here we have only one parameter, lambda, which you can relate that to any moments of the distribution, be it the first moment, mean, or any other higher moments like variance, skewness, etc. So that is what we normally do. So the point here is that any theoretical distribution will be having some parameters, maybe one parameter, two parameter, three parameter. And when we want to fit that, or when we want to fit that particular theoretical PDF to any time series, the ultimate job is that we have to estimate the parameters of the distribution. And how to estimate these parameters? There are well-known methods like method of moments, method of likelihood, L moment method, and then there are advanced methods like Bayesian inference method and all that, so on and so forth. So these parameters need to be first of all fitted for us to fit a particular theoretical PDF to any time series. Now moving on. So as I mentioned, once we fit the time series, once we fit the probability distribution function to any time series, how we can pick up the extreme is that all we have to pick up is the tail of this particular distribution. For illustration, I have shown you the typical distribution of temperature, how it varies. Often, despite the geographical location, most of the time temperature follows a bell-shaped curve like this, and it can be fitted probably to a normal distribution. And this right tail defines the hot extremes, and the left tail defines the cold extremes. And precipitation is a little bit tricky because the shape of this varies, depends a lot based on the geographical context. So for example, this is a typical distribution of precipitation, and if you want to pick up the heavy extremes, we have to go to the right tail side. So once we know which distribution is best fit for a particular time series you are dealing with, once you fit that, you can go to the tail values to pick up the extreme events. Or you can define a threshold also. For example, a percentile value, more than 90th percentile, more than 95th percentile, more than 99th percentile. That is the way we define and pick up the extremes from the distribution. Now, how we can pick up the extremes from the time series itself? So for example, here, I am showing you the daily precipitation time series of just 3 years. And how we can pick up the extremes from the time series is, there are two majorly adopted, frequently adopted techniques. One is the annual maxima method or minima method, or it is also called as block maxima method. For example, if I am considering the first year, then the annual maxima is something like this, right? And the second year, the annual maxima is something like this, and third year, the annual maxima is something like this. So these maxima values, or even it is applicable to the minima values also, can be picked up. And further, we are only worried about these extreme events or the annual maxima events. That is the extreme time series only we are going to talk the modeling about. Now, the disadvantage of this particular method, annual maxima, or even it is called block maxima. In this particular example, I have shown the block as the annual period. Block can be anything as defined by the user, any time duration. Now, in this, the disadvantage is that, for example, in the second year, see, this particular event is not actually picked up by the annual maxima, whereas you can clearly see that this particular event is much larger than this particular, the maxima which is picked up from the first year, right? So that is what is the main disadvantage of this method. Some of the peaks or the maxima will be actually neglected if you go for the annual maxima method. That is when this peak over threshold method is adopted, where user can define a threshold like this, as shown as the orange line here, this line. So, and all the values which are falling above that particular threshold will be picked up, and that time series is called as the extreme time series, which will be used for further modeling purposes. Now, the point here is that when we go for the annual maximum method, we are picking up one value per year. So the one value of 1 year is not going to be dependent on the other value of another year. So in that way, if you go to the annual, if you adopt the annual maximum method, then the independency between the events, which is a most important assumption in all these kind of time series modeling, all these particular events should be independent of each other. I hope you must have also heard of something called IID, independent and identically distributed events. So that kind of assumption will not be violated in annual maxima, whereas over peak over threshold, this might be violated because we are picking up peaks which are lying very close, during a particular year. So after the pickup of events using a peak over threshold method, we have to check the independency or the dependency in the time series, and if it is independent only, then only we will go ahead with the modeling purpose. So otherwise, we have to think of methods on how to remove this particular dependency from the time series. So these are the two methods we usually adopt. And then, as I mentioned, so once we pick up these time series or the extreme time series from the actual time series, now we are only worried about this, the extreme time series, the maxima time series or the minimum time series. Now, which distribution it will fit into? We have already seen that the frequently adopted distributions like normal, log normal, gamma, exponential, etc. But then these particular frequently adopted probability distributions may not be a good fit to the extremes we have picked up. But then there is a beautiful theorem which actually simplifies all these procedures. The theorem is called Extremal Type Theorem, EVT. So the extremal value types theorem. So what it says is that if we pick up these high observations or the extreme values or the extreme high or extreme low values, and we should not worry about what parent distribution comes from. That means what is the actual distribution the time series was modeled, that we don't have to worry. But once we pick up these extreme values, despite the parent distribution, these extreme values are going to fit into one known distribution, a single distribution, a generic distribution. So as closely as m increases. So the only criteria is that we should have large number of those particular extreme values. So always these extreme values, despite the parent distribution it is coming from, will tend to closely follow one known distribution, a known distribution. And what is that known distribution? This known distribution is called a generalized extreme value distribution. So generalized extreme value distribution or GEV distribution, I will be using this abbreviation quite frequently in the later slides. So GEV distribution, the expression is something like this. Capital F, as I said, it denotes the CDF, X is the variable, and the parameters mu, sigma, and eta. So this is a 3-parameter distribution. Mu denotes the location where the distribution is going to be located. Sigma denotes the scale parameter. That means the spread of the distribution it will denote. And the eta denotes the shape parameter. It can take a skewed value or a right skewed or left skewed or a normalized value, something like that. Essentially, the shape of the distribution is defined by the shape parameter. So this is going to be a 3-parameter distribution, and it is actually a generic distribution. So depending upon the value of these parameters being taken up, this particular GEV takes up other sub distributions. For example, if this shape parameter is equal to 0, then GEV will be converging to a EVD type 1, that is extreme value distribution type 1, which probably you might have heard something like the Gumbel distribution. So whenever the shape parameter is equal to 0, then the probability distribution or the extreme distribution will converge to a Gumbel distribution. And the Gumbel distribution is the most frequently used extreme distribution, and sometimes it is called as the extreme value distribution. So when the shape parameter is greater than 0, then it is called EVD type 2 or Freshet distribution. When the shape parameter is less than 0, then the GEV will be converging to a type 3 distribution or something called as a Weibull distribution. So in hydrology, if you scan through the basic hydrology textbooks, it all says that in hydrology, we commonly use this Gumbel distribution for the extreme value fit, and also the Weibull distribution. Freshet is most rarely applied in our field. So moving on, so then now we know if we have a time series, how to pick up the extremes from that and which probability distribution it needs to be fitted to. And once the probability distribution is fitted, now we also know how to go to the tail and analyze the tail or the common parameters of the distribution. Now, why we are so much interested in modeling these extremes? Why is it so important? We have the time series already, right? So now why we have to fit into a probability distribution and analyze the character characteristics of the distribution. That is what is given here. So there are many applications of modeling these extremes. A holistic analysis and modeling of extremes is at most necessary for proper planning and management of water resources. So the main application which we are going to deal in this lecture is the development of IDF curve, or the intensity duration frequency curve, which we civil engineers all are aware of. Now let's have a peek into what is this intensity duration frequency curve and refresh this idea. So intensity duration frequency curve is a curve with the rainfall intensity in the y-axis and the duration in the x-axis. And this curve, there will be many curves representing this frequency information. Or frequency information is often given in the form of a return period. And return period is nothing but you can say that as for example, a 1 year return period indicates that that particular event is on an average will be repeated every 1 year. That doesn't mean that it will happen every year, but on an average it will get repeated every 1 year. So this is the way frequency is represented in IDF curve. And if you can look at this if you can see this particular figure, then you can see that as rainfall intensity, as duration increases, rainfall intensity is decreasing for all the curves. For all the despite the return period, rainfall intensity will be decreasing as duration increases. That is a common thing which is expected. And also for a given duration, for example, say this 30 minute duration, as the return period increases, the rainfall intensity will increase. That means return period increase means, for example, 10-year return period and 100-year return period. Of course, we know that the 100-year return period is going to be an extreme event, or the rarest of the rare event, and when compared to the 10-year event. So for that means the intensity of that particular rainfall is going to be much higher when compared to the 10-year rainfall intensity. So these are some aspects you can see in the intensity duration frequency curve plotted from over any region. As duration increases, rainfall intensity decreases, and for a given duration, as return period increases, rainfall intensity increases. Now, if we have this curve and how to develop this curve, I will discuss in the later slide. But if we have this curve from the extreme time series, we have extracted from the actual time series. Now, how to use this? This IDF curve is usually used for the construction or the design of any urban infrastructure or any infrastructure, any hydraulic infrastructure. So for the design of any hydraulic infrastructure needs something called a design rainfall or design rainfall intensity. So for example, the usage of this IDF curve is normally like the input variable. We have to have a fair idea about the duration of the rainfall event and also the return period. Now, once we know the duration and the return period, corresponding rainfall intensity can be picked up from the IDF curve. Now, how will we know the return period and the duration? Return period is mostly defined based on the life of the structure or the importance of the structure. The more important the structure is, the more high the return period is. And the more high return period, we are going to design the structure for a more high, heavier rainfall intensity or the heavier rainfall event. And so that the return period can be defined based on the life of the structure, or as I said, the importance of the structure. And how will we find out a typical magnitude or the value for the duration of the event? Duration of the event is, say for example, the place at which we are going to design or construct the structure. And we will have the catchment area contributing to that place, right? The outlet, consider that place as the outlet, and we can always delineate the catchment area. Now, if we can find out the time of concentration, that means the time taken by the rainfall when it occurs at the farthest point to flow through the catchment and reach the particular location. That will give you an idea about the duration of the duration which we have to consider. So once we know the duration and once we know the return period, then from these kind of curves, if those are available, then we can pick up the rainfall intensity, and that is how we go for that is how we estimate the design rainfall intensity. So ultimately, the bottom line here is that if we have to have this IDF curve for all these design purposes, and that is when we're going back, we have to fit we have to extract the extreme events from the actual time series, and we have to fit a probability distribution. We have to find the adequate or suitable probability distribution, which is going to best model those extreme time series. So with this background, so then how to model these particular extreme events. There are different approaches. Often we go for this so-called univariate or multivariate approaches. In univariate approaches, as you have seen that in IDF curve, there are mainly 3 variables, but then the modeling is, the curve is fitted for intensity versus rainfall for a particular return period. So at least there are 2 variables, rainfall intensity and rainfall duration. And the rainfall intensity and rainfall duration are related to each other. They are not independent of each other. So as we have seen that as duration increases, rainfall intensity is going to decrease for any geographical location. So, but then to simplify this modeling, we often adopt this kind of univariate approaches. In univariate approaches, and that too when we use that for the IDF generation, IDF development, we consider rainfall intensity as the only variable or rainfall depth as the only variable, and we neglect this particular duration. That means if you can look at this particular, if you can see this particular plot, this is the details of the rainfall event happening, and then this is probably for a 50-hour, that means for almost 2 days, and in this one we pick up the extreme events. So we have this information for a long time, and we pick up the extreme events from this time series, and that particular event, just one event or 2 events, would be using for picking up rainfall intensity of different duration. For example, this one will give you an idea about the rainfall intensity or the maximum rainfall intensity of 1 hour duration, and the same event will be used to define the rainfall intensity of 2 hour duration, 3 hour duration, or 24-hour duration. What is happening here is that this event is actually ending, starting from 25 and ending in 30, and then there is a huge gap or a dry spell here, and then the second event is happening. But then when we are deriving the rainfall intensity or the maximum rainfall intensity, for example, for 24 hours, if we are picking up 24-hour duration rainfall intensity, when we pick up, we are actually considering 3 separate events. So these events will be having different characteristics, and we are combining all these events to when we actually try to adopt this kind of univariate modeling. But the bottom line is that in univariate modeling, we're going to only consider one variable, and you now know how to pick up that variable, which is rainfall depth, from an event series like this. Now going to the bivariate modeling, and bivariate modeling is the one which is needed for development of IDF curves. So it actually gives the joint distribution. As I mentioned, the 2 variables are there, rainfall intensity and also the rainfall, the storm duration. These 2 variables will be picked up from the time series. I will show you how to pick up simultaneously, keeping the event characteristics intact from the time series in the latest slide. But once we pick up that rainfall intensity and the associated duration, then we will either go for this any of the joint distribution. That means rainfall intensity series is there and the corresponding storm duration series is there. Now we have to find out the joint distribution of these 2. So joint distribution is nothing but the way I have shown you the relative frequency plot. That is a 1D plot. Now we have 2 variables. This will be a 2D plot. So that 2D plot, if you are drawing, that will give you an idea about the characteristics of the joint distribution. And then you can either fit that distribution in an exponential model, then that will be bivariate exponential model, bivariate log normal distribution, bivariate gamma distribution, whichever distribution it is best fitting to. So now the drawback is that, so there are many studies which have used these kind of distributions, exponential, log normal, and gamma, to fit the rainfall intensity and the actual storm duration. But the problem here is that, as you know, when you fit a joint distribution, the assumptions are that these 2 variables you are fitting should be independent of each other. And also these 2 variables should follow the same distribution. For example, if rainfall intensity is following a log normal distribution, the storm duration should also follow a log normal distribution. Then only you can fit a bivariate log normal distribution. So the drawback is that in practical cases, these 2 variables, intensity and duration, are of course going to be dependent on each other, and the marginal distribution or the independent or individual distributions of intensity and duration are going to be, most of the time it is going to be different. So then there comes the beautiful concept of copula, how we can find out the joint distribution or the evolution of these 2 time series together, the joint characteristics, I should say. So then I am not going into the details of copula. That itself is a very large topic. But then the concept of copula is that it is a function which tackles this kind of dependency and also the individual probability distribution, or the different marginal probability distribution in this time series. So it is a function that joins or couples these one-dimensional marginal distribution of multiple random variables, and it has some equations behind that which will actually give us the joint distribution function. And by handling these dependency and also the individual or the different marginal distribution. So it will give us a map like this. This u and v are the variables we are considering, and this z-axis will give us an idea about the probability, and this the joint distribution is expressed as a surface map like this. So that is some concept we'll be using later, but we'll not go into the details of this copula. So there are, as we mentioned, there are two two approaches, univariate and bivariate, or rather multivariate modeling. But then if you look back, whatever we have discussed, the gist of that was we have a rainfall time series or event time series. We now know how to pick up the extremes from that, and we now know which distribution it is need to be fitted, and we now also know which modeling to be adopted, whether it is a univariate modeling or a multivariate modeling. Then from where these kind of words like stationarity and non-stationarity are coming into picture, why we have to focus on all these things. So we already know the distributions, right? We have even copula also with us. So why should we worry about this stationarity and non-stationarity? What exactly these terms indicate? So let's have a look at on why we have to focus on. So that is when we have to have a fair idea about the recent increases in the extremes, majorly attributed to the climate change and also the anthropogenic actions, because of the anthropogenic actions. So are these extremes really increasing? That is what we have to first of all scan through the time series of observations before jumping into any kind of stationary and non-stationary analysis. So if you look at the literature, there has been a lot of reportings in the news articles, and there have been a lot of articles being published, especially after 2000, reporting that there are increasing amount of floods across the world, and also there are heat waves, etc., etc. And also if you look at the scenario of India, the reportings of the flood from one or another place is becoming an annual phenomena right now. And for some of the places like Northeast, it is an annual phenomena. Every year it gets flooded, Orissa and all. So these kind of flood, there is a threefold increase in the occurrences of floods over India in the recent decade. That is what is reported. So definitely these kind of extremes, the reporting say that they are increasing. And then let us have a good look into, first of all, convince ourselves that these extremes are increasing. That is what I'm going to show in the next 2 or 3 slides. So if we have a global picture of temperature, this picture most of you might have already come across. So the temperature is shooting up even in the observed period, and if you look at the projections for different scenarios, depending upon the severity of the scenario, the temperature is actually going to shoot up a lot, like 3 degrees Celsius or 4 degrees Celsius. So this is the global average surface temperature change for different scenarios. Whichever scenarios we are adopting, then also we have to face an increase in the temperature. Now, when we look at the global precipitation, here this particular period is the mid-century, that is 2046 to 65, and this is the late century. And on the y-axis is the return period, and the the box plots represents different scenarios. So despite the scenario, if you, for example, let's focus on the green one here. So here the return period was high, and then the return period for the same event decreases. That means the recurrence interval is decreasing. What does it mean? Recurrence interval means the same intensity rainfall is going to repeat much frequently in the late century than how it was occurring in the middle century. So that means the extremes, the frequency of the extremes, or the return period of the extremes is actually, or the recurrence interval of the extremes are actually increasing. So that means more and more extremes we have to face in the future. So this is the global picture, and let's have a good look into the picture of India. So I will, even though our focus is on precipitation, it is worthwhile to have a look at the temperature also. So here we have the maximum temperature, daily maximum temperature, and the daily minimum temperature. We all might be facing an increase in the temperature in terms of the heatness index, but then the analysis we have done was based on the diurnal temperature range. That means diurnal temperature range means in a day, what is the difference between the maximum temperature and the minimum temperature. So the difference between the maxima and minima in a day, that is what is called diurnal temperature range, or DTR. And this figure shows the evolution of this diurnal temperature over the past half century. That means 1951 to 1980, 51 to 1990, until 2010. So you can see that the red one increased the shortening up and the blue one increased the dampening out. So this particular, so you can see that the red one is actually covering the whole of India as we have moved across this past half century. So in some regions, as I have indicated here, there is a dampening out, but let's see what is the reason. So this is the DTR, diurnal temperature range. So most of the region diurnal temperature range is increasing, and some region, for example, the Rajasthan regions and all, there the diurnal temperature range is decreasing. And what is the reason for that? So this is these are the plots where we related the DTR with the maximum temperature and DTR with the minimum temperature. Let's focus on this figure first. So DTR is increasing. That means that these only considered the grids which have where the DTR is increasing. So when the DTR increases, we have seen that the Tmax is also increasing. That means the maximum daily temperature is also increasing. When the DTR is increasing and the T minimum may not have a major role. So as I mentioned, DTR is the difference between Tmax minus T minimum, Tmax minus T minimum, and the increase in DTR is due to the increase in the maximum temperature. So the maximum temperature is increasing. And also, if you look at this figure gives you the DTR decrease. So the DTR decrease, whenever DTR decreasing, there is a increase in the minimum temperature. And whenever DTR is decreasing, there is not much contribution from the maximum temperature. So both these things, whether it is DTR is increasing or decreasing, if the DTR is increasing, then it is due to the increase in the maximum temperature. If the DTR is decreasing, then it is due to the increase in the minimum temperature. So in both ways, maximum temperature and minimum temperature are increasing anyways. So that means the higher the hot extremes are definitely going to increase, are definitely increasing. That is what is observed from the observed data. Now let's take a peek into the precipitation scenario. So this is a study by Vittal and others in 2014. They specified that if you actually see the spatial mean of total rainfall, the spatial mean might be increasing in the first century, that first half century, from 1900 to 1950, and then it is decreasing in the later one. And also, if you have a look at the spatial mean of extreme rainfall, that means the 95th percentile, then also it was increasing in the earlier one, and it is sort of decreasing, but the slope is reducing in the later one. But the most important thing is the heavier extremes, that is 99th percentile, the heavier extreme events or the heavy rainfall events. That was increasing in the earlier one also, and that does increase in the later one also with a higher slope. But this is a very brief or broad study, and this study was refined, and it was by Vinna and our study from our lab in 2015. So what we did is that we analyzed various aspects of this extreme rainfall series, or the rainfall series, and we picked out the wet days. Wet days means this is extreme wet days. Wherever, whenever the rainfall is greater than 90th percentile, that is the definition of wet day we have given. And whenever these kind of days are occurring simultaneously, that is the definition we have given for wet spell. And the dry day we have defined as less than, whenever the rainfall is happening less than 2.5 mm, that is a dry day. And the consecutive occurrences of those dry days is defined as a dry spell. So the message here is that if you look at the dry regions, there is a positive trend of wet day and spell, and then there is a negative trend of dry days and spells. And if you look at the wet regions, there is a negative trend in the wet day and spell, and then there is a positive trend in the dry day and spell. So that probably indicates that the wet regions are turning drier and the dry regions are turning wetter. So there is a notable change in the regional monsoon system, and the point here is that all these kind of changes are going to affect the modeling, or the when I say the when fitted probability distribution function, these kind of changes are going to affect the modeling or the simulation of these events. So so we have a fair idea that over India also these kind of extremes are increasing, or rather I should say changing, and in an abrupt way. Now, why we are focused on these urban regions? How these kind of extremes are going to change in the urban regions, or is it anything going to be different from other regions? The answer is yes, because that urban regions, there is one phenomenon called urban heat island. So urban heat island occurs because the temperature of the city, when it compared to the rural area or the suburban area, it will always be high. So the city experiences a much warmer temperature when compared to the suburban area or the adjacent rural area. And why is it so? Because of this built infrastructure, the materials that we are using, like the pavement, the steel and the brick, they are often grayish in color or black in color, and they reflect more heat. So more heat will be generated, and this of course will shoot the temperature up. So more paved, so that is how the temperature is high in the urban region, and that is what is called urban heat island. And that has an impact on the precipitation also, and or rather the flood events also. The precipitation, even we are assuming that it is going to be same, if you are assuming a scenario like that. And then since in the urban regions there are more paved areas, and there will be more runoff and less infiltration, so the amount of flood events or the urban flooding events are going to be much higher in these areas when compared to the rural area, where the water can penetrate down or infiltrate down. And now I mentioned that we have assumed that the precipitation is going to be same. That also will not be occurring, because as you know that the temperature is shooting up, then the air parcel which has a higher temperature, as you know that it has a capacity to hold up more moisture. So that is defined by this Clausius-Clapeyron rate. That is approximately per degree rise in the temperature, around 7% of the moisture will be more in that air parcel. So this urban heat island, the moisture, depending upon the moisture availability, of course, that is going to be much more in the air. And that, of course, depending upon the availability of, again, the precipitation nuclei and all, that will cause much more convective storms, local convective storms over the urban area. So the urban area, it's like cocoonized area, then with a higher temperature and probably with more convective rainfall storms, which of course will increase the flood events, or rather we call this the urban flood events. So this is going to be the urban scenario. And this is the reason why the extremes, whatever we have discussed, if you look at a zoomed in level or a local level, the extremes are the change in the extremes is expected to be much more than when compared to the changes we have seen for the rural areas, or on a much more broader scale, which I have shown earlier. And now this particular scenario, the attention on these urban extremes need more highlight, because this is an interesting picture released in 2016 or so. This shows that this particular figure shows the global map of all the urban agglomerations with more than 750,000 inhabitants in how it was in 1950. And you can focus your attention over India, probably over Mumbai and Kolkata, where the urban agglomerations with a high population. And this is a projection which they have done in 2012. For a projection for 2025, the entire India is getting, have all those dots with various coloring intensities. So the darker color indicates more population. The darkest one is greater than 10 million, and so on and so forth. So the entire India, probably most of the places are getting urbanized. So they said that in 2008 itself, when they took a statistics, more than half of the world population is now living in the urban centers, and this proportion continues to grow. If you look at the NCT Delhi, also the population over the past years, that is shooting up like anything without giving a proper attention to the constraint of the resources. So 3/4 of the world's urban population and most of its large cities are now in the low and middle income nations. That is another reason to concern. Even though this urbanization is increasing and most of the population is moving to the urban cities, and that is happening in the low and middle income nations, where we know that these kind of flood events or the disasters have much more devastating impact when compared to the developed countries. So the proper attention or highlight to all these things, and all these factors need to be accounted when we talk about these extremes and extreme modelings and so on and so forth. So the gist of the discussion just now we had is that whatever probability distribution we had fitted into the extreme time series or the tail of the distribution, that of course is going to be changed. The distribution. Yes.
Kuldeep Tiwari ji, please switch off your audio, please. Dr. Kuldeep Tiwari.
Shall I continue?
Yes, madam. Yes, madam.
Yeah. So this particular probability distribution is expected to change, and how that change will happen, that is what we have to understand. So there might be a positive shift in the mean. So if this solid one is the observed one, that means in the observed period, and so it might have shifted to the left. Then that means there is an increase in the magnitude of cold extremes. I am again showing this temperature PDF as an example. The same can happen for the precipitation probability distribution also. If it is shifting to the right, then there is an increase in the magnitude of hot extremes. And also, not only the shift like this, there could be also a change in the variance also. That means dampening out or a stretching up. So the increase in the variance also increases the spread of the distribution. So the increase in the variance, what it happens is, for example, in this figure, the illustration I have given, it will actually result into an increase in the frequency of extremes in both the tails. So all these kind of properties or the changes in the PDF or the probability distribution function, we need to first study before accounting that in the modeling. So that is the change in the statistical parameters over time is visible in the observed data also. So that is where this concept of stationarity and non-stationarity comes into picture. So let us first have a brief idea about this stationarity and non-stationarity is. So if we have a time series, and if we can, for example, if we have the precipitation time series from 1900 to 2020, and we can break up into many realizations, that is from 1900 to 1930, 30 to 60, 60 to 90, so on and so forth. So these time series, we can call that as realizations of this precipitation series. And if I am fitting a probability distribution for each of these realizations, essentially, if these probability distributions are the same, that means the characteristics of this probability distribution, or rather the parameters of this probability distribution are the same, then I can say that the rainfall series or the variable is going to be a stationary one, and I can go with the stationary modeling. So stationarity definitely gives you an idea about the stability or a static nature of the particular variable. So the probability distribution itself should be same when if you are taking up many realization of the same variable. That is the definition of stationarity. And accordingly, there is something called, for example, if it is a normal distribution, which we are going to fit for the time series, and as I mentioned earlier, normal distribution, there are two parameters, mu and sigma, and we have found that mu and sigma are not changing across the time for various realization. Then we call that as this variable as a strictly stationary or purely stationary variable. But in some occasions, if you find that only mu is changing and the variance is not changing, mu is the first order moment and the variance is not changing, then we call that as a first order stationary variable. If the mu and sigma, if sigma is not changing and mu is changing, then we cannot call that as stationary. So if one parameter is changing, then we call is not changing, then we call that as a weakly stationary. If all the parameters, that means the entire PDF is not changing, then we call that as a purely stationary. So in short, for a series to be stationary, this PDF of the variable at a time should be equal to the PDF of the variable at a later time for all the time periods. That is what is indicated here. So for example, if the PDF is shifting like this, then that means the variance is stationary here, but the mean is not. Here, the second example is like the mean is not changing, but the variance is changing. That means the mean is stationary, variance is not. So this is the kind of inside stationarity also. This is the kind we can define the stationarity and order the stationarity. First order stationarity, second order stationarity, and so on and so forth. Now the opposite of this, that means if the parameters are changing with respect to time, then we call that as a non-stationary series. And the non-stationary series, it's a very simple concept. So the statistical properties of the time series, if it is changing or varying across the time, then we call that as a non-stationary series. And the change can be happening because of any trend, increasing trend or decreasing trend like this, or because of any jump in the series, and because of the seasonality issues also. So it could be anything, and it could be these kind of trend, jump or periodicity can result from even the climate change or global warming we have just discussed, or due to any other anthropogenic actions also. So basically, what the message is here is that if we find that the statistical parameters are changing with time, then the past statistics will not give a good basis for making predictions about the future. That is what needs attention here. And the non-stationary model may not assume the procedure is in equilibrium with respect to the statistical properties over time. But then we have to use the time series somehow. We have to extract the information of time series. That is when this kind of non-stationary modeling comes into picture. So if we have a time series, and most of the time we are focusing on extreme time series, so how we can detect this non-stationarity? Detection of non-stationarity, if you look at the basic probability books, there are many. First of all, there will be kind of visualization. If by visualizing the series, if you are seeing a trend, then it could be because of the non-stationarity. If a seasonality exists, but then there is no noticeable trend, then it could be a time series. So visualization is the first thing we do for detecting the non-stationarity. There are other methods also called the autocorrelation method, partial autocorrelation method. Autocorrelation is nothing but the correlation with respect to that time series, or rather the lagged time series. So when you plot the autocorrelation function for different lags, if the autocorrelation is dampening out and coming to zero quickly, that means probably the time series is going to be a stationary one. If the autocorrelation is fluctuating like this and it is not dampening out or coming to zero, then that means there is some periodicity, or rather there could be some non-stationarity in the time series. So there are other methods also. I'm not going to the details of that, but ultimately, if you look at the literature, often in all the research articles, the stationarity or the non-stationarity is detected by analyzing the trend, the presence of trend. So if there is a trend, they say that there is non-stationarity, and if there is no trend, then they assume that the variable is stationary. That is the simple method they have. Most of the studies have used, and that is what we are going to question in the later slides. So now, so once we detect this non-stationarity, then how to model that? So as I mentioned, after extracting the extreme time series, we will be fitting that to any GEV distribution like this. This is the full equation, the full form of the GEV. Earlier I have shown only this form, but this is the full form of the GEV. And as I said, this is a 3-parameter distribution. And these 3 parameters, based on the definition of the non-stationarity, these 3 parameters should vary with respect to time, isn't it? So how to model that time variance of these parameters? So for example, mu is going to be a function of t, sigma is going to be a function of t, and also the shape parameter is going to be a function of t. Now how to model these? What equation we will use? There are different equations. So for example, most of the time in all the literature, you will see that if you want to express the variation of mu or the non-stationarity in mu, the parameter mu, we often go for a linear trend. That means mu x is equal to mu x t1 plus mu x t2 into t. So basically here, it's a function of t. That means t is the covariate here. As the time moves on, this mu, the parameter also moves along or varies along with t. And that variation, we are assuming that it is going to be a linear one. So what we are doing here is that we have only we had 3 parameters, but even the first parameter mu, when we account the non-stationarity, it is getting split up into 2 parameters. So the number of parameters are actually increasing, and the complexity of the model is actually increasing. And rather, as I can say, that the uncertainty in the modeling is also increasing if we adopt the non-stationarity. Please remember this one. I will talk about this in the next slide. Now, this is the concept of stationary and non-stationary model. Stationary model, we had a PDF, and as we move across time, For example, if this particular dotted line denotes the design flood, and as we move across line, that particular probability is going to be constant because the PDF is going to be constant and we don't have anything to worry. But in non-stationary model, this is the PDF which we started. But then as the time moves on, this PDF, I am only showing the shift in the location here just for illustration, but there could be, as I said, shift in the variance also, shift in other parameters also. So if the shift in the variance is only considered, then the PDF is going to shift by a time period, right? And see the design flood. The design flood was this value, and as we move across, the design flood, whatever value, if you had adopted the stationary modeling, that now in this at this time period, it is more or less like an average flood event. So, which of course is going to topple the structures. The structures which might have designed with this design period will of course will be seeing much failures as we move on to the future. This is the basic definition, and since this is a linear thing, that is why we have assumed mu is equal to mu xt1 plus mu xt2 plus into t. That is a linear variation. So often the linear variation justifies as far as the location parameter is concerned, and I have seen for the variance sometimes a exponential, a simple exponential or power law will serve the purpose. But essentially it is going to be a function of t. As time increases, as we move to the future, these particular parameters are going to change, and that is how we are going to accommodate this particular. That is how this non-stationary modeling is done. So it's a very simple concept. I hope you understood that. I'm not going into the mathematical complexities of that. I'm intentionally avoiding that, but the concept, I hope it is clear to you. Now, I mentioned earlier that when we shift from a stationary to non-stationary modeling, one parameter is actually increasing into 2 parameters or more than 3 parameters, and it increases the complexity or the uncertainty of the modeling. And these kind of things, and also the presence of the non-stationarity, how to detect that, that also is not well defined. So these kind of complexities or confusions in this particular topic make water managers to debate on this topic. One school says that we don't have to consider the non-stationarity. One school says that we have to consider the non-stationarity. So for example, there are well popular articles like the stationarity is dead. We have to go for non-stationary modeling, and what will happen to water management. Another school of thought says that stationarity is undead. That actually thought mainly comes from because of the increase in this parameter and increase in the uncertainty, and also the time series, once the non-stationarity is detected, after some time it says that it is not non-stationary. So a proper detection of non-stationary and a refinement of all these methods we have been using in the literature, that need to be defined. But necessarily there is always these 2 schools of thought here, and this is the explanation for that. So for example, when we say stationarity is dead, why we are saying that? Stationarity, as I mentioned, it actually denotes a kind of a stable equilibrium or a static thing. So stationarity is equivalent to static nature. And we know that the real world is not static, it is going to be dynamic, as we have seen from the earlier pictures. Also, temperature is increasing, precipitation is changing. So we cannot assume that the world is going to be a stationary one or a static one. So we have to go for this non-stationary modeling. That is the debate of the first group. And the second group says that unstationarity is dead. So for example, stationarity, according to them, is, of course, they are right also. It is stationarity and non-stationarity. It is not, we cannot say that it's a stationary world or non-stationary world. World is of course changing. But then the model we are applying, we can apply probably a stationary model to a non-stationary world also, dynamic world also. So the terms are only restricted to the modeling and not to the real world. That is a justification these people are giving. And in one way that is also right, because when we come to the modeling, sometimes these kind of stationary simple models do give better solutions than the non-stationary modeling. When we actually take a trade-off between the complexity and the uncertainty, as I discussed earlier. So their argument is that if the change can be predicted through this kind of deterministic terms, then better go for a simplified modeling. So ultimately, the detection of the non-stationarity is most important, and that too the realistic detection of the non-stationarity is important. So first of all, we have to check that whether non-stationarity is evident from the historical data or not. So as I mentioned, the traditional method, even adopting this non-stationary modeling, what it does is that it takes a time series it checks for any existence of trend, and if a trend is there, then they go for a non-stationary modeling. And how do they go for the non-stationary modeling? They of course change the parameters in the probability distribution function, as I mentioned. And which parameter to change, they don't know, because there is a trend in the model. So what they do is that, for example, if there is a trend in the model like this, an increasing trend, it could be probably result in the change in the mean also, like this, a shift in the mean. But then there may not be any trend in the series. Then also we have seen that there may be a change in the variance. So there are two things here. A trend in the series may not be reflecting as a change in all the parameters. And also the change in the parameter, any parameter, one or more parameter, may not be reflecting as a trend in the time series. So these two are often related, but not necessarily. But that is the methodology traditionally in the literature. You will see if there is a trend, they go for the non-stationary modeling. And what they do is they change all these parameters, and they, for example, mu changes, sigma changes, mu changes, shape parameter changes, sigma changes, shape parameter changes. So they play with all these combinations, and then they model with all these combinations, and then they select a model which is the best model. That is the normal procedure adopted for non-stationary modeling. So there is always a lack of knowledge about which parameter is changing, and this is where we are trying to bring realism to. So the traditional non-stationary model, I'm going to abbreviate that as traditional NSM, non-stationary model. They consider only the temporal variation of any local parameter or different combinations of distribution parameter. But when we address this non-stationarity, as I mentioned, that the studies so far have addressed by changing the location only. Most of the studies have only changed the location when they see a trend, or at the max they have changed the location and scale parameters. And often there are many studies which try all these parameter combination. As I said, mu changes and sigma changes, mu changes and shape parameter. So all these parameter combination they create, and they make model for all these parameter combination, and they select the best one based on some information criteria. So based on some performance measures, as you can mention. I'm not going into the details of all these things. So such approaches actually increase the complexity. You have to try a lot many models, and then there is a lot many uncertainty in the modeling. And so there is a lack of any realism in bringing out the non-stationary characteristics of time series. So we are going to address that, and then so this, how to bring realism in the detection of non-stationarity and incorporate it in the modeling. That is the first question we will address before I show how to develop this particular concept and develop the IDF curve. So the methodology developed is something called a time sliding window approach. So we go with the basic definition of non-stationarity. What it said when we defined the name non-stationarity. To define the non-stationarity, we should actually ensure a change in the parameters or a trend in the parameters, not necessarily in the time series. So we try to extract the parameters from the time series. So for example, if you have a time series of precipitation for the last 50 or 60 years, we split that up into many realizations. For example, as I said, 1900 to 1930, then 1910 to 1940, something like that. So time sliding window we adopted, and each of these realizations, we found the best distribution. So the distribution, for example, if this particular, all the realizations are fitting into some GEV distribution, and then we will, so these are the N realizations or the M realizations we picked up from the time series. And each of these realization, we are going to fit into a most appropriate distribution. And that is the appropriateness of the distribution. There are well-defined tests like chi-square test and the KS test, Kolmogorov-Smirnov test. Again, I'm not going to the details of that. So there are some methods to find out the appropriateness of the probability distribution. So we found the appropriate probability distribution, and we took out the parameters from this realization. So for example, we have the realization one, first realization, we took out the parameters of the probability distribution function, and from second realization we took out the parameters of the probability distribution function, so on and so forth. So in this one we are going to use the GEV. So for example, if you take out the parameter mu, you will be having m number of mu's from these m realization. So that is going to be the time series or the series of this parameter mu. Now in this series, if there is a trend, that is what we have checked. So this goes back to the basic definition of non-stationarity, that we have defined that if there is any change in the parameter of the distribution, then only non-stationarity exists. So that is what we have tried. And if there is a trend in the parameter series which we extracted from the various realization, then we go for a non-stationary model, and that too only for that parameter. If the second parameter is not exhibiting any trend, that means that parameter we will be modeling as a stationary one. So that is the kind of the approach which this time sliding window gives. And if it actually shows a trend, then of course a linear trend like I have shown here will be used for non-stationary modeling. So this is the gist of this. In this explains the traditional method. Traditional method says that time series shows a significant trend. If it doesn't, then go for a stationary model. If it shows a significant trend, then go for a non-stationary model. But then how to model these parameters? Either adopt the non-stationarity in all the parameters, or one or two, or try the combination of all these parameters and go through all those complexities and select the best model. So but then these kind of differences occurs because as I mentioned, the trend may not always reflect in all the parameters, or the change in parameters may not get reflect the trend also. So that is when this proposed method compute the trend in the parameters of all these parameters separately by splitting the main time series into main realization. And if the parameter shows some trend, then that particular parameter will be modeled as a non-stationary one. Other parameters which do not show any trend will be modeled as a stationary one only. So this particular technique, the applicability of this technique, we have demonstrated using some 4 synthetic time series. That means no trend here, and trend in mu, and so here there is no trend in the time series, and here also there is no trend in the time series. Here these 2 time series B and D have trend. So if you go for the traditional method, these 2 time series B and D must have been modeled as a non-stationary one, whereas A and C will be modeled as a non-stationary one. So here, when we analyzed this GSW, we saw that this does not have any trend, and the mu and sigma also doesn't have any trend. So in our approach also, this will be modeled as a stationary one. But in this one, there is a trend, and the trend is visible in the location parameter, but there is no trend in the sigma. This has a trend, but that trend is not visible probably in mu, but that trend is visible in the sigma. So something like this. And this also has a trend, and trend is available. Trend is present in both mu and sigma. So the first one, no trend in any of the parameters. Second is trend in mu and no trend in sigma, and trend in sigma and no trend. So all these combinations we try to generate using the synthetic series. And then these are the differences between the models adopted by the traditional and also the time sliding window. So for the traditional one will model the first one as stationary. Our model also will model the first one as stationary. The traditional one will model the second one as non-stationary, but then they have to go through all those combinations, mu and sigma, and finally when we adopted that technique, the best model we got as non-stationarity in mu only, and in our approach also it is non-stationarity in mu. The third one, it is a stationary one according to traditional, but in our one there is a stationarity, the non-stationarity in sigma. So the present model will be a non-stationary model in sigma, and the other one there is non-stationarity in sigma and mu, and our model also non-stationary sigma and mu. But wherever the models are same, there the approach we have adopted, that will be much quicker than the traditional one where they have to try all the combination and find out the best fit. Now, probably I thought of addressing 2 issues here using this approach and a bivariate model, how to generate the IDF curve and also how to incorporate the information of climate variables in this time sliding window approach. But I will see how far we can go. So going to the first one, using this GSW approach and bivariate modeling, we selected 4 urban areas: Bangalore, Mumbai, and Kolkata and Madras. And here Mumbai receives the highest rainfall, followed by Kolkata, and Bangalore receives the least rainfall. And as you know, the Madras receives rainfall from northeast monsoon, and Bangalore also apart from the northeast monsoon, whereas Bombay and Kolkata, it is majorly from the southwest monsoon. So what we did is, since this is a bivariate modeling, we have to extract the intensity and duration from the time series. So let this be the event series we are considering. This is the first event, this is the second event. We have to extract the duration and intensity from this one. So the definition of this particular events, how we can consider this as separate events. So if there is a minimum duration of dry spell, should be something like the concept of inter-event time definition. So there should be a minimum time between these events, then these events can be called as separate events. And what should be the basis of that inter-time? It is actually based on the time of concentration. But then for us to make the time of concentration, we have to do the hydrological modeling of all these 4 stations, which is not going to be possible. So we went into the literature, and the literature suggested that for small urban state catchments, the time of concentration is generally less than 6 hours. So the IETD, or the inter-time here, can be taken as 6 hours only. So we took that 6 hours, and so if the interval between 2 events is more than 6 hours, then we consider that particular event as separate events. Now, once we identify the separate events, then if a storm commences and then there is a wet hour, for example, the duration of the first event, that is the storm duration. So for example, the first event, the storm duration is D1, second event, the storm duration is D2, and the depth accumulated from this storm event is, say, capital D1, and the depth accumulated from the second event is capital D2. And once we extract these attributes from this event series, then the storm depth divided by the duration should give us the storm intensity. So what we are doing is, we have the precipitation event series. We are converting that into 3 attributes or 2 attributes, storm depth and storm duration, and the storm depth will further be converted into storm intensity. So finally, we will be having 2 series with this storm intensity and storm duration. Now we have to pick up the extremes from that. So how we have picked up the extreme is that we have picked up those events where the storm depth is greater than 90th percentile. So that is the definition of extremes we have given. And so whichever events are where the storm depth is greater than 90th percentile, we picked up those events, and the corresponding duration and the intensity are saved as 2 time series. Now we are going to play with these 2 time series only. This is the gist of the events extracted. So as you can see that Bombay, we are retaining these old names because that is how the stations are known now also. So the Bombay, the duration is going to be, we have experienced very high large duration events, whereas in Bangalore, the duration is very less. But you can see that according to the intensity is always high, more or less high in Madras when compared to the other cities. So there are these 4 cities, even though those are urban regions, then also the characteristics of these extremes are going to be very much different. And these are the number of events we have picked up for the event, for the modeling. And now, once we picked up these events, storm duration and storm intensity, we have to find the marginals of this. So for the marginal, normally gamma or log distribution is used for storm intensity, and exponential is used for storm duration. That is what we could pick up from the literature. But to be more realistic, what we did is we picked up this 8 basket of all the distribution, these 8 distribution, and then we fitted this storm intensity and storm duration to these 8 distribution, and find out the best distribution using KS test and some information criteria. KS test is called McGraw-Smirnov test. So these tests are available for us if you want to pick up a ideal or best fit PDF, then you can always use this kind of test. So from this basket of probability distribution, finally, this is the one we have received. So for example, for Bangalore city, the intensity, we have found that GEV is the best distribution, and most of the cities we got GEV as the distribution for intensity. For Kolkata, it is a little bit different, and further you will say that Kolkata time series itself is much more, is quite opposite when compared to the other urban regions. For duration, most of the cities gives log normal as the distribution. So in GEV, we have 3 parameters to fit. In GP, we have 2 parameters, and in log normal and gamma, we have 2 parameters. We'll be fitting those parameters further. So now that we have fitted these marginals, we have to see how we can find out the joint distribution of this. Before that, we have to see that how this duration and intensity are related to each other. So these, for example, let's concentrate on the Bangalore city. The storm intensity marginal is this one, as we have described just now. Storm duration marginal is this one. Rather the relative frequency histogram, you can say that. So if you actually plot a scatter plot of duration versus intensity, this is the behavior of Bangalore, and the Bombay behaves like this, and Calcutta like this, and Madras like this. So you can see that storm events are most of all concentrated near short duration. There is a high density here in Bangalore. In Madras and Calcutta, it is more or less dispersed. And in Bombay, you can see that if you look at the duration, it is going till 200 something, whereas for other regions, it is much less. And also the correlation coefficient. All these are negatively correlated, as we have discussed. Duration increases, intensity is expected to decrease. So the correlation is much more significant for Bangalore, around 0.63, minus 0.63. And for Calcutta also it is minus 0.71, and for Mumbai it is 0.34 and 0.57. But necessarily all these correlations are significant. So there exists a relationship between these two parameters, these two variables. That means they are not going to be independent. And also we have seen that the marginals are GEV and log normal. They are not going to be same. They are not same. So we have to use this copula approach for us to come up with a joint distribution. Copula approach, there are many copula family, and in hydrology we mostly use the Archimedean family. So since the correlation between intensity and duration, as just now we have seen that it is negative, and it is significantly negative. So there are only two families here, this Ali Huck and Frank copula. But Frank is the most frequently used, and it can also model a significantly negatively correlated variables also. So we went on with the Frank copula, and it is a one parameter copula. It again simplifies the complexity. So we need to only model for one parameter. So this is the equation. U and V are the variable, and theta is the parameter of the copula. It is nothing but a joint distribution. You can just imagine this is a joint distribution function or a PDF function with the variables as U and V and the parameter as theta, nothing more than that. So, but then we already know that these two variables, intensity and duration, are related. So the conditional Frank copula or the conditional probability distribution, which you all might be aware of, that also can be expressed something like this. That means fxy divided by fx into fy, right? So that is the way we define this conditional probability distribution. So once we fit this in this particular, we now have the marginal distributions of these two variables, intensity and duration, and also we now know how to fit into a copula. But how to model this non-stationarity? That means the theta of the copula and also the parameters of the GEV distribution and the log normal distribution, or any other distribution for storm intensity and storm duration. So whether we have to model that as non-stationary or stationary, that is the question here. So the TSW approach, which I have discussed earlier, that is implemented here for this series: storm intensity separately, storm duration separately. And this is the first panel. This is an illustration for the Bangalore city. So this first panel gives the idea of the variation of parameters for Bangalore city. So you can see that the location parameter is increasing. This is for the storm intensity. Mu1 is increasing of the GEV distribution. Sigma 1 is also increasing, and the shift parameter is also increasing. And this panel is for the storm duration, where these two ones are for the storm duration, where I think log normal is the best fit distribution. So mu d, that is location, is decreasing, and the sigma variance is increasing. And this is the parameter for the copula, that is theta. There is a decrease, but the slope is very less, and so the star, wherever you can see the star, that implies the significance. So here also there is an increase, but it's not significant. Here also there is a decrease, but this is not significant. But all other parameters, there is a significant increase or decrease, and these parameters should be modeled as a non-stationary one. So this is the complete picture of all the stations here. So you can see that if you focus on the location parameter of storm intensity, you can see that all these stations, the location parameter is increasing. So there is a shift, and the variance or the scale parameter actually is increasing for almost all the cities, but Kolkata, as I said, it always show a contradictory pattern here, an opposite pattern. And the shift parameter in most of the we pay little attention or lesser attention to the shift parameter, and the duration also you can see. So if you actually have a give a close look to all these variations of parameters, you will see that the short duration events or short duration intense events might be increasing in the future for all the cities except probably for Kolkata. That's a message one may get from by analyzing, and these also will give you an idea about which parameter we have to model as non-stationary and which parameters we can keep as a stationary one. So this is the essence of what we have discussed. So Bangalore, as we mentioned, it is DEV for intensity, and in that mu I represents the parameter corresponding to the intensity, and D represents the parameter corresponding to the duration. Mu I is increasing and it is significant, sigma I is increasing and significant, and this one is also significant. Mu D, the duration of the location parameter of the duration is decreasing, and sigma D is increasing. So this is the essence of which parameter we need to model as non-stationary and which parameter we can keep it as such, that is stationary. And the Frank Coppola, surprisingly, this the theta parameter, we have seen that for any of the station, the theta parameter is not increasing, not changing. So in the exercise we are going to do, we are going to take this theta parameter as stationary for all the stations, because that is something we have seen from this figure. Here, 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 and here. Theta parameter, there is some increase and decrease, but nowhere it is significant. Other parameters we will model accordingly to the non-stationary and stationary. So we also did the traditional NSM to compare how this particular method is going to be different. The models we are coming up with this new method, TSW approach, how it is different and how it is possibly efficient when compared to the traditional non-stationary method. What traditional NSM is going to give you, which model, and what this particular realistic, more realistic method, as we claim, is going to give us. That is what we have discussed. So in the traditional method, as I mentioned, if there is a trend in the time series of the original time series, then they play with all these kind of different combinations of these parameters, and also the best model will be selected based on some information criteria. And when we did this traditional non-stationary model, we observed significant trend only for the storm intensity and storm duration of Bangalore, and only for the storm duration of Kolkata. That means for all other variables, that means storm intensity, storm duration of Mumbai, Chennai, and also the storm intensity of Kolkata, will be modeled as a stationary one if you go for the traditional NSM. And we will see what difference it is going to make. So this is the essence of what we have discussed. So the methods we are going to adopt is that, so all these things, Kolkata, this one is stationary, everything is stationary. Whereas in this particular modeling, all these names, non-stationarity in one or more parameters will have to be accounted. And main thing is that we can focus on this one. After doing all these combination, the traditional NSM gives a best model as non-stationary, and that too the variation in sigma and mu is accounted, which the new this method, a realistic method, is also coming up with. So some places the models are the same, but the approach, I would again say that is more quicker in this one, because we directly approach the parameters and see the changes in that. Now, all these parameters are estimated using a Bayesian inference. Often the parameter estimation is done using maximum likelihood method or method of moments or L moments. I'm not going into details of any of these methods. All these are available in any traditional books. But in this one, so all these methods gives a parameter that just is one value. That will not give the uncertainty in the parameter, whereas some method like Bayesian inference and all will give the distribution of this parameter, what is the possible fluctuations in this value or the range of this parameter, that will be given. So we use that method, and then we calculated the return period. Return period we have defined earlier. It is the the average recurrence interval, and it is nothing but the inverse or the reciprocal of the exceedance probability. So if we have the probability or the conditional probability, 1 minus that will be the exceedance probability, and the inverse of that should give us a conditional return period, and also the joint return period can also be calculated. Now return period is calculated, and the rainfall intensity or the variable corresponding to that return period is called as a return level, or the return level is the quantile corresponding to the exceedance probability of a specific return period. Non-stationary return level of return rainfall intensity is also, we want to check how the intensity has varied for a particular return period. So all these characteristics are calculated after this time series. The rainfall intensity and duration time series are fitted through a copula function. So I am going to straight away show the results here. So results, this one is the storm intensity and storm duration of all these 4 cities from the marginals. So you can see that these are for different return period, or so for example, you can see that the lower one is for 10 year, the middle one is for 30 year, and the upper one is for the 100 year. So storm duration, if you see, has a storm intensity has an increasing trend, and it is evident from the return level of all these cities, Bangalore, Mumbai, and probably Madras. It is more or less same, but then for Kolkata, this is decreasing. And as you can see that wherever the storm intensity is showing an increasing trend, storm duration is showing a slightly decreasing trend. That is expected because these two are negatively correlated. And for Kolkata, storm intensity is decreasing and duration is a little bit increasing. So what does it mean? That intensity is decreasing, but then the duration is probably increasing. That also may result into some extremes, but as I mentioned, Kolkata should always show a different pattern when compared to the other urban area. But the other one, you can see that, for example, 100-year return period, the storm intensity is increasing. So more and more intense rainfall is going to happen, and the storm duration is decreasing. So for Madras, we have seen that there is not much change, significant change, while there is a little big change in the decreasing trend in the storm duration. So that means even if the intensity is not changing, then also there is a constraint or the restriction of storm duration. So this is what the information we have extracted from the marginals. And let's have a look at the joint return period. This is an interesting picture, but it will be a little bit difficult to understand here. So this duration, this is for the Bangalore city. Duration is in this axis, intensity is in this axis, and the return period is in this axis. So this is a total idea of the joint behavior of duration and intensity. So the map, the black map here gives you the result from the non-stationary model. That means the TSW model. And the blue ones gives the traditional NSM model, the non-stationary model, which is used traditionally. So here we can see that in Bombay and Bangalore, the non-stationary model, that is this TSW model, gives a lower recurrence interval. You can see that the blue lines are higher than the black envelope. So that means the black model, which is the TSW model, it says that the recurrence interval is much less than the stationary model. What does it mean? The recurrence interval means more frequency of extremes. So that means from this TSW model, it is saying that the extremes given for a particular value of extreme, particular intensity, that will be repeating at a higher rate than the what is suggested by the traditional non-stationary model. And that is the same for Bombay also. But for Kolkata and Madras, it is the opposite. That means the traditional non-stationary model is saying that the recurrence interval is much less when it compared to the TSW model. And it is same for Kolkata and Madras. But for Madras, these extremes are same, but if you actually zoom out an area here for around 100 return period or so, that will be, so this is the one. This is a zoomed off area of this particular portion, around 100-year return period. There it is saying that the blue ones, that means the traditional NSM, This is the Madras one. This is traditional NSM is the recurrence interval is much higher, and the TSW, the recurrence interval, is much lesser. So in Madras, it is a conflicting, I mean, it is a mixed behavior. For some of the period, recurrence interval is higher. For some of the period, recurrent interval is lesser. But for Mumbai and Bangalore, this new model says that the extremes will be increasing consistently. So here, this is a evolution of return period. So the evolution of return period over time for some of the duration, that means 1 hour, 48 hour, and for maximum duration for all the cities. So this is the year how the return period is evolving over the year. So as you can see that Mumbai, the return period is decreasing, and here this is for 1 hour, 48 hour. This is for 1 hour. This is for 48 hour, and this is for the maximum duration, whichever the maximum duration rainfall which is observed from the time series. So let's concentrate on this 1 hour because that is of importance to the urban area. Of course, all other things are, but let's focus on this. So the 1 hour duration rainfall was the return period was decreasing. That means the recurrence interval, it is actually increasing. The frequency is increasing. It's the same for Bangalore and Mumbai. As we expect, the Calcutta says that the recurrence interval is increasing. That means probably the short duration events are going to be less frequent. And the Madras is more or less a stationary thing. That is not much change. So this is the kind of short events. The high intensity rainfall will increase here, and that will eventually increase the flood peaks in the urban catchments, and that needs to be accounted in the design of the structures. And this is yet another view. These are some, what we did is we picked out some observed events. That means Bangalore, there was a flood event in 2017, and it was of 129 mm depth in 24 hours. How the return period of this particular event is varying. And Mumbai, we picked out the 2005 event, and Madras, we picked out the 2015 event. And these three are shown here. So these events itself, from the time series, you can see that itself is also, this return period is decreasing. That means it is getting more and more frequent. So these were extreme events. If you remember, all these events happened over these cities. These were widely reported and made devastating effects. So those kind of events are also increasing according to this particular approach. So the decreasing trend is around 0.54 year per year, and Mumbai, the trend decrease is much higher. And this year also we have seen that how the urban floods have come there. So 1.5. So Mumbai might be witnessing a more recurrence of these kind of floods when compared to other cities. And Madras, a little bit of decrease is there, but the rate is very less. So, and these are the details of all these bivariate intensity duration NSM. So let us first understand for one city, and then we can extrapolate that to other cities. So here, I am going to highlight the 100-year return period. For the 100-year, these figures are given for the 100-year return period. That means the rarest of the rare, should be the rarest of the rare event. So for the 100-year return period, this is the return level we have plotted, and this is the duration. So if we focus on the 1 hour, so the duration for 1 hour rainfall of 100-year return period, the return level is around 100 millimeter per hour. And that, if we are seeing the evolution, that is going to increase here. This is a red line here. So the difference, so here the red one, the solid red one, gives you the variation of this return level versus duration according to the TSW model. And the black dots gives you the variation of this return level versus duration using the traditional NSM. So if you take the difference between the stationary and the non-stationary return level for a 100-year event and for a 1 hour duration, that is around this difference, 100 minus around 60 something. So that is around 33.45. That is the kind of underestimation it will give if we go for a stationary approach. Now we can imagine that this kind of magnitude, 33 or 40 millimeter per hour, if you are designing with that underestimation, what is going to be the impact on the structural design? And also, so this is all about this particular figure. And also this RL for 1 hour, I have blown up, and the further details of this 1 hour duration is given here. So the 1 hour duration, RL versus RP, that means return level versus return period. So you can see that the box plots gives you the non-stationary approach, and the star, that is asterisk, the green one gives you the stationary one. So always these green ones are underestimating or giving lower values than the non-stationary approach for various return periods. Not only for the 100-year return period which I have shown here, but for all other return periods also, the level or the intensity for 1 hour duration is going to be much more. And what is the difference? That difference is shown here. That means the difference between the mean value and this value, that difference is shown here. And as you can see that as the return period increases, that means as we are talking about more and more extreme events, the difference between these two methods are going to be increasing. So the more important the structure, the more relevant this approach is going to be. So in short, the short duration events intensify at a faster rate than the long duration events, which is shown here. And also, as the extremes, the return period increases, the difference between these two particular approaches are going to be much more significant. This one is for the Bombay station, which essentially conveys the same picture, exactly same picture. And the stationary assumption will underestimate the flood peak in both of these highly urbanized metro cities, Bangalore and Mumbai. Kolkata, as I mentioned, it always showed a different pattern. Like this is the stationary approach, that is actually more just opposite to what we have seen in the previous slides. And also these green ones are above the blue box plots. So, and the differences are always negative. So stationary RL is higher. Stationary assumption probably will be, so that means that in this historical scenario, those events might have occurred. Probably that is going to be dampening out in the future. So again, when you decide, that is not going to be a realistic one, because you might be over designing the structure for. And the Madras is more or less exhibits a stationary approach. So you can see that both these models are almost coinciding with each other. So probably for Madras, even though some events are reported, the modeling can be done even using a stationary one, and that will also differ for different durations. We have to see that. So changes are probably more dominant in shorter duration. Here some changes are there, but as the duration increases, it is more or less coinciding with each other, regardless of whether it intensifies or subsides. So this is the approach we have discussed, the gist of all the things we have discussed so far. So takeaway is that a dynamic copula-based bivariate or multivariate extreme event modeling is developed, and it offers time-varying joint return period and return level with its uncertainty bounds. And we have also seen that there is considerable differences in the return levels between the traditional and TSW approaches, and this needs to be given utmost attention in the design of urban infrastructure. So this topic is about application of TSW on bivariate modeling, and we have also seen how to develop this IDF curve. I will also give in the next slides, if you remember, the way we have modeled this uncertainty is that mu is equal to mu x1, mu xt1 plus mu xt2, mu x2 into t. That means only the time is taken into account when we modeled the non-stationarity. But then, so that means time only we have taken as the covariate. Our next question is that, can we use the information from any climate variables? So because the climate variables often capture this non-stationarity in a much better way than what the time series itself, whatever we are dealing with, might be giving. So whether we can use those climate variables also as covariate in the non-stationary modeling, that is what we have dealt with later. But I will only brush through this in some 5 or 6 slides. So what we have done is we of course kept the the earlier urban areas we have discussed, and we have added some more urban areas also. And then we, because we are adding some more teleconnections, that increases the complexity. Instead of going for a bivariate modeling, in this case we went for a univariate modeling, the one I have discussed in the second or third slide, only by picking up the rainfall intensity from the time series. So the various other covariates we have considered is that the local temperature, which will give us the local surface temperature changes, the global temperature, which will give us an idea about the influence of global warming, DTR, which I have explained earlier. DTR is having a huge impact on urbanization, soil moisture and humidity. ENSO Modoki, ENSO in the El Nino Southern Oscillation, which all of us are aware of. But there is a new index Modoki, which gives us the relative warming between the tropical Pacific and the Western tropical Pacific, and also the IOD, Indian Ocean Dipole. So all these five, I should say the climate variables we have selected, and we just checked whether these five can give some additional information and can make the IDF curve a little bit more realistic. So in addition to these five, we have also used time as one of the covariates. Time cannot be neglected ever. Time is a covariate that should be there for all the non-stationary modeling. So what we did is that we extracted the time series, rainfall series, or rainfall intensity, as I have explained earlier, for different durations. Here we have not classified into events. So we are going to again try the univariate modeling here. And we picked out the annual maxima rainfall for each of these duration. So for each of the duration, 1 hour, we will be having one value for 1 year. So we'll be having one such values for all the years, and that is the time series we are going to deal with. And that is the time series where we have to assess the non-stationarity. So for each of the time series, we have assessed this non-stationarity, and if there is any non-stationarity or trend in the parameter, we of course use the TSW approach. And if there is a non-stationarity, we went for stationarity. If there is no non-stationarity or trend, we go for a stationary model. If there is a trend, we went for the non-stationary model. And I am straight away showing here some of the results. So this is the characteristics of the annual maximum rainfall intensity for different duration. As I mentioned, we have picked up the characteristics for different duration, like 1, 2, up to 48, not in a continuous manner, but in a discrete manner. And this is the annual maximum rainfall intensity series. As we know, as we expect, the intensity decreases as duration increase. And it's the same for almost all the Kalka region. And so this is the annual maximum rainfall intensity series, which we are going to play with. And we fitted the non-GEV technique. GEV technique, as we know, there will be 2-3 parameters to fit. And we use that TSW approach. And I'm going to give you the essence of that. For example, Bangalore city, all these parameters, mu is increasing, sigma is increasing, and the shift is not changing. And what we did is that we, instead of this, this is for only the GEV one. And for Bombay, this mu is increasing, sigma is increasing, and shift parameter, there is no change. So this TSW approach will give us an idea about which parameter is increasing, which parameter is decreasing, essentially which parameter we need to model as a non-stationary one, and which parameter we can keep as a stationary one. After that, to model the non-stationarity, as I have discussed earlier, we have to express these parameters in terms of some equation with respect to t. Earlier we were using mu1 plus mu2t, but instead, still here we are trying other covariates also. So mu will be expressed in terms, not only in terms of t, but also in terms of these 5 covariates. That's the only difference here. So instead of the mu turning up into 2 more parameters, here, depending upon the covariates, there are many other parameters. So there is an added complexity. That is the reason we have gone for a univariate modeling, because bivariate modeling here, it's possible. We are doing that, but then explaining it here, it's going to be much more complex. So I am sticking to univariate modeling here. So the only difference here when we add the covariate again is that the transformation of this equation into many more segments like this. So what we did is that we went up for a different combinations of these covariates and also time as a covariate, and we also considered stationary model also. And from all these basket, from all this basket, we have picked up the best model. That's the essence of it. So this one will give us an idea about what is the best covariate, and this will also give us an idea about which covariate is influencing the rainfall intensity much more dominantly, and what is its relation with respect to the duration. So let's first understand this figure. These different colors are given for different covariates, and this color is given for the stationary model. And this one, 1, 2, 3, this gives the duration. So for example, if we focus on Bangalore, 1 hour duration rainfall, the best covariate is this one. This one means EMI, Enso monarchy. And also this one, LTA, local temperature, and also even the time. Similarly, if you go for 48 duration, GTA, global temperature anomaly, is the best covariate, is one of the covariate, and also EMI, and also IOD, and also this LT. So this is the information. This information is getting from this figure, and you can see that if you analyze for all other cities also, you can see that as the duration increases, the local processes dominate. For duration increases, the local processes or the global processes dominate for short duration. So the local processes are dominant for short duration, whereas the global processes are probably dominant for longer duration. So that is the one interesting result we received. For example, if we are focused on a short duration rainfall, we can even constrain our covariates to the local ones. We don't have to worry about the global ones there. Whereas for longer duration, we certainly have to consider the global processes also. And this is a 1 hour the climate informed covariates. I will just skip this, and then this is the essence of this. So this is the curve for different duration. This is the return level for different return period, 2, 5, 10, 15 up to 100 year. So the as mentioned, the same as the earlier figure, the box plot is a non-stationary and the green one is stationary. You can see that for the illustration of Bombay, the difference of 1 hour duration here, this is the 1 hour duration with the 2-year return period, the difference is much higher. And as we increase the duration, the difference is getting lesser, dampening out. And this is more or less the same for all other cities, Bangalore and Madras, except for Calcutta. Calcutta I will show here. So the Calcutta, this is the picture. So this, you can see that there is not much difference between the stationary and non-stationary. For example, 1 hour, 2-year duration did not undergo any changes probably. And the decrease in the non-stationary return level for higher duration, that means these are almost zero, negligible. So Calcutta, even after accounting these climate covariates, it exhibits a contrary pattern with respect to other stations. So takeaway is that the significant non-stationary in the distribution parameter, especially in the scale parameter, is evident in all the cities, except probably for Calcutta. And also these covariates we have added have more influence on the extreme intensities, where in Calcutta, again, there's a difference. And the traditional stationary based IDF curve, we have to update that with the non-stationary based IDF curve, that is for sure. But then when we use this non-stationary method also, we have to make it much more realistic, so that the design and the construction will be much more using the reliable design rainfall. And also, as you can see that there is also a great amount of research now also needed to reduce the uncertainties in these approaches and come up with some robust techniques. So with this, I think I will stop, and will be happy to take up any questions if you have, or any suggestions if you have. Thank you.
Excuse me, ma'am.
Yes, please.
Yeah. Thank you so much, ma'am. Actually, from day one, I was eager to hear your talk. So I'll start with my queries. Actually, myself is Aarti. I'm a research scholar from SVNIT Surat.
Hello.
Yeah. Ma'am, it's like how to conclude the best covariate, as just now we have seen in your slides. So the diagram which you have shown for 1 hour, 2 hour, 3 hour, and the best covariate. Yeah, ma'am. So how one can conclude on the best covariate?
So best covariate, what we did, Aarti, is we tried up with different combinations of these covariates, and we come out with various models. And that I have not explained in this one, but you will get that from our publication, the details of that, but I'll explain it here. So how to come up with best covariate is to try up with various combinations, and then we selected the best model based on some information criteria. So often I omitted that detail also. That is probably the reason why this doubt arises in your mind. So there are something called information criteria, BIC, DIC, etc. Based on which we select a best model. That means which model is actually giving more information among the set of models we have selected. So from that model, whichever model we have got as the best ones, which covariate combination that model is using. From there, we have picked up the best covariate based on that analysis. Is that
Yeah.
clear?
Yes. Now it's clear, ma'am. Thank you. And ma'am, one more thing that we have used the hourly time series of rainfall.
Yeah.
And as you have mentioned in one of your slides, there were some missing years also.
Yes.
So as I am also struggling with that, how we can justify the missing years and taking it as a continuous time series?
No, it's not a continuous time series you need for this kind of modeling. I understand that the doubt you may have, for example, you are picking up the extremes from the time series, right? And we are, these all modeling thing which I have shown is on the extreme time series, not on the actual time series, which is continuous. And the assumption we are we are keeping here is that all these variable or the values we are picking up are independent of each other. It should be independent of each other. So if we are missing, if we have a missing year in between, that is not going to affect that. But essentially, the effect would be that it might be making, for example, in that particular year, if an extreme might have happened, you might be losing that data. But definitely, it's not going to affect the continuity, because continuity is not needed in this kind of analysis. Is there a confusion there, Aarti?
Yes, now I got your point exactly,
Yeah,
ma'am.
so
Yes.
you are picking up the events, and these events are independent of each other. So if at all one event is missing, you will of course lose one information, but it is not going to affect the modeling.
Yeah, exactly. Yeah. And ma'am, when we talk about the peak or threshold series,
Yeah.
so as the traditional method given in VT Chow, if the entire data set we fill decreasing order, and however the number of series, select that as a threshold and take that series as a partial duration series, if I talk about it. And how we check the independent or dependent event in such a series if I go with a calendar year.
If you go with the question is not so clear to me, but what you are probably, can you please repeat what VT Chow
Yeah.
said, partial duration?
Yeah, ma'am. If I say 40 years data is there, so if a 20-hour data is there, annual means daily maximum value, and if I arrange in a decreasing order that data set, and whatever the highest 40 values are there,
Right.
I will select, and 41th value will be my threshold.
Right.
So, but the limitation will be that the event should be independent.
Right.
And what I feel that rainfall, daily rainfall, if I say, it should be independent event, or again in that I have to check whether the data or the events are dependent event. For example, if in one day, 2 extreme events are there. So one is in the morning, one is the evening, or in the span of some hours.
I understand.
Or consecutive event, if I say 24 hours.
Right.
So should it be like dependent or independent?
So ideally, in all these modeling, especially this kind of probabilistic stochastic modeling, we have to assume this independence, right? The events we are selecting, or the one event to another event, should be independent of each other. That means there is no redundancy of information coming in this one. But then, as you said, rightly said, there are many ways of adopting this POT. Like you said, arrange that in the descending order and select this number of events. That will ensure that the number of events can be same as the number of years you have. But then there are other techniques, like I can even select a threshold value, 90% threshold, the way we have selected, which may give us some consecutive events also. As you said, which the two extremes might be occurring in one day itself. But then those are not independent of each other, might not be independent, because the moisture which is coming from might be coming from the one source, and the moisture, but some percentage of moisture might be poured out as the first event, and the rest of the moisture might be poured out as second event. So essentially dependency will be there. And there are some tests of, so what we did is that we did some test of dependency. So you will find that in the traditional books also. There are some tests for dependency. That means taking the difference between the successive events and then plotting a normal plot like that. So, and also there are some methods to get rid of this dependency. So we have not done that, because in our series, even though we have extracted the storm events which are adjacent to each other, we have found that, you remember the inter event time, right? 6 hours and all. So that probably
Yes.
have saved us that, to ensure that all these events are independent of each other. And there are,
Okay, so
yeah,
when
you
you
check on the methods. There are some methods to check the dependency of this particular time series, that you have to check. And if there is some dependency shown, then we have to know how to remove that dependency.
Yeah, sure, ma'am. And ma'am, when you say the 90th percentile events in the POT,
Yeah, please go ahead.
so that 6-hour difference, the justification which was there in the minimum time duration, inter-event time is 6 hours. So that will suffice that events, means like taking that series of 90th percentile. That criteria we need to check.
What we did is that the sequence is like this, Arti. You have the actual series with you, right?
Yes.
And then first step is to extract the storm events.
Yes, ma'am.
So we have extracted all the storm events. It's not the extreme storm events, all the storm events based on this IETD, inter-event time definition.
Yes.
So, and after extracting the storm event, then we are picking up the extreme storm event based on this 90th percentile depth.
Yes, I got it. Yeah.
Okay.
Thank you, ma'am.
Other way around. Yeah.
Okay, thank you, Aarti. I think let's have one more last question, because time is up. And we have already given that email ID also of Madam.
Yeah.
So those who wants to interact directly, if any detailed things are there, she's, I think, she's helping a lot.
Yeah,
Dr. Punita, wants to have some query?
Yes. Good morning, sir. Good morning, ma'am. It was a very informative lecture, and I got to know that I have to read a lot in this. Ma'am, I work on urban heat island. Like, I have worked in Delhi region, and currently in Punjab also I'm trying to work on it. But I have never explored the urban hydrology part of urban heat island studies. So mine was more on this aerosols role and the land use, land cover changes that are affecting the urban heat island. So, ma'am, could you please, at least let us know some of the scopes where I can.
But recently we did an activity, but then I didn't proceed that because it was not my expertise mostly, but probably you can explore. So you are working on aerosols, and you probably is from the atmospheric domain. That's what I'm presuming. So what we did is, there is something called a land surface model, especially designed for this urban area. It is a community land model only, but the urbanized part. So that will take into account this UHI. That means essentially we have to model these feedbacks, right? As I explained, the urban area is expected to heat up. So
Yes,
the temperature, the local temperature is certainly
will
going to be
increase.
much more than the suburban area, that you already know. And now how it is going to impact the precipitation over that area, that this model will be helping us. For example, this model will be able to give us run some simulations, like if the amount of urbanization is increasing, then what is going to be the changes in the hydrology of that area through this particular modeling. So even that model, if you are aware of land surface models specially designed for the urban regions. There is a abbreviation for that, I forget that. I think we have indicated CLM only, community land model, but then the urbanized portion of that, where these kind of feedbacks, urban UHI and all are fairly good, reasonably modeled. You can even think of clubbing that LSM with an atmospheric model, so that these convective precipitation events, which is expected to increase, that could also be modeled. And then since you are using an LSM, it has a hydrology portion also. That will be help. There is a lot many. When I say like this, it may seem that it is easy to model, but these are very complex models.
Yes, ma'am.
So, but this is one thing you probably can explore, which can couple this urban, integrate this urban hydrology with the UHI and aerosol. Yeah.
Sure, ma'am. Sure. Thank you, ma'am. I'll bother you in future also if I
Sure,
need.
pleasure.
Thank you, ma'am.
Please
Thank
feel
you.
free to.
Okay, thank you. Let's end up the first session. We are already, I think, approaching next session. Thank you, Dr. Dhanya, for a nice presentation, and also, yeah, one more session will be there tomorrow.
Yeah.
On some other topic. I think during that time also, you people can interact more with Dr. Dhanya. Thank you, Dhanya. Thanks.
Thank you so much, sir, for taking this much time. And tomorrow's presentation, I promise that I will keep it very general. Will not be mathematically intensive at all. But see you guys tomorrow also. Thank you.
Yeah. Bye.
Thank you, ma'am. Thank you, sir.
Okay, thank you. Friends, we will be having a break now. And note that next session will start exactly